if I can do that. Okay, so it looks like it's recording. So let me just get onto the right page on my practice here. So 533. So we're still on chapter 2 extended. Okay. So let me just share. So what we're going to do today, we're going to do some of let's see. Given the function. Why do I not have the right thing? That's where I don't think I want that. So hold on 1 second. Because I wanted how to take a derivative. Yes, that's what I want. Okay, so hang on, let me just fix this. So big picture, we're going to do some more practice with limits, and then we're going to start doing the different rules. So you can see how much easier it is once you do the different rules. So let me just duplicate this, and then I'm going to get rid of what I have written on it. Okay. What is going on? Technology is great until it starts to misbehave.
Mhm.
Let me go there. Let me go here. There. Okay, so that's what I want. So now I just need to make a blank copy. For the class, I would say just talk amongst yourselves for a second.
Yeah, I'll just talk to myself, the voices in my head.
I know. How are your classes going?
Oh, they're going.
Do you like being the lead?
No, not in the slightest. There's so many changes this year. And we have a math night coming up next week that no one's really helped me plan. I've never planned anything like that before. So I'm like, okay, well, we're just gonna, I don't know, I made a plan and people are gonna execute it, I guess.
Oh gosh. Well, you know what? We have Poonam has come on. I thought she wasn't in the class, so we may have company after
Oh,
all.
cool.
Let's see, I just let her in. So Poonam, I didn't think you were taking the class.
Dr. Riley, I'm so sorry. I thought I dropped it and then it
Uh-huh.
it did not. I don't know what happened. And my, like when the phone updates, my Outlook was logged out.
Uh-huh.
Thank God something came up and I'm like, I need to check my email. And then I
So
realized I did not drop your class.
so do you need to drop it?
No, I think I will do it because then if I finish this class, I get my 18 credits, which I'm looking forward to getting it all together
Okay.
to apply for college adjunct positions.
Right.
And that's it. And again, working with you is not, it's going to be honored. So not a problem. But can you believe, I'm so sorry. You would think like this woman has been like not even like I felt so bad. Now I'm having some back issues, so I have been seeing doctors in the evening. So it's just stressful. Nothing sad, but just stressful. Yeah.
Well, fortunately, last week, there's only three of us, three of you guys in the class, four counting me. But last week I was able to videotape the class, and I'm
Yeah, I saw
videotaping
the
tonight.
YouTube
So
link.
that's
I will go through it. Yes.
okay. So I just need to contact them to tell them that you're coming because I had said that you weren't coming. So I have to update that somehow. So I will figure that out. So what we're doing today is so we're in chapter 2, but chapter 2 doesn't go through the derivative rules. So I
Mm-hmm.
made a whole packet that's just called chapter 2 extended. So, and Poonam, this is Sarah. Sarah, this is Poonam.
Hi,
Hi.
Sarah.
So Sarah's teaching middle school and she's also the lead teacher. So that's what she's up to. So far she's been a gem with calculus. We figured it out. So so you can check and see what you're behind on because you need to submit a couple of things.
Yes.
So just
So
kind of check that and just, do it as you go along.
I just needed a clarification for the journal article. I couldn't find any the information. I read through it. Anyway, I started reading
So
yesterday.
you want to get a journal article that is from a peer reviewed.
Mm-hmm.
So get a math journal and then
Mhm.
get an article that pertains to something in math that maybe you'd be teaching. So something that is you find interesting. It could be calculus, but it doesn't necessarily have to be calculus. And then follow the rubric for the rest.
Sure.
Okay.
Sure. Okay.
And
Yeah,
nothing,
thank you.
so nothing is due next week for both of you guys. In terms of this, what's due in our schedule. So the historical paper, which is from that Math Through the Ages book, is not due until class 6. So that's what's on the horizon. So I think I've posted enough things. I've kind of figured out enough of what I have on our new program. So hopefully that's clear. So I don't know if you had a chance to download these notes, but you may want to just kind of copy along as we go. So we're going to start now. So what I said was find this derivative using limits. So I actually started writing it out. So that's your kind of skeleton. So then you're going to continue. So we can race. Let me just take my bracelet off here. Okay. So if you're going to continue from there, what you would do is you would square everything in the parens. So that's going to give me, remember, we're still going to write down that we're doing the limit as h goes to 0. And then it's going to be x squared plus 2xh plus h squared. Now, where my
If you're
kids
showing anything, we can't see it.
oh, I'm so sorry. Perhaps I should share the screen.
No worries.
I know. It's been one of those days. Okay, let me do this, and let me do this and this. Okay, so let me open this up now, and we're here, and we are here. Okay, so that should good. Is that a whole lot clearer?
Yes.
Okay, good, good, good. So that's where I'm starting. So then I'm going to keep going. So where my kids tend to mess up is they don't like to distribute the negatives. So they like to do other things with them, not clear what, but definitely distribute the negative. And that should be a 7. Let me go back, make sure that looks like a 7. H, and then plus 3, and now I'm distributing the negative again. Negative x squared, positive 7x, and then minus 3. So here, at this point, I'm going to go ahead and cancel out these, and we're good about where they came from, right, Sarah?
Mhm.
The denominator, we're good?
Mhm.
Okay, so then I'm left with an h here. So at this point, what should happen is everything that does not have an h attached to it should cancel. And that's kind of your litmus test. As long as that happens, then you know you're good to go forward. If at some point it doesn't happen, don't go forward, go back. It's probably a distributing a negative type thing. So here is negative 7x, and there's a positive 7x. Here is a positive 3 and a negative 3. And then here are my x's, opposite signs. And then when I look, everything that remains has an h in it. So then my next step is going to be to rewrite it. And I'm going to kind of combine two steps. I'm going to factor out an h, put a big bracket, and I'm going to distribute, kind of undistribute as I go. Okay, so that's going to be over h. Okay, so now at this point, because I can cancel the h, you're ready to take the limit because you can plug in a 0 right here and not have any algebraic police issues. So when I look at that, what's going to happen now, let me go back to my color. So I can say, okay, let's take the limit as h goes to 0. So it's going to be 2x plus 0 minus 7. So that's going to equal 2x minus 7. So in terms of like the reasonableness test, if you know your first function is a quadratic, then your derivative should be linear. So that's one thing you should kind of say, okay, that worked out well. Okay, so Poonan, do you remember taking limits? It's probably been a while since you've done limits.
Yeah, I do remember a little bit. It will come back to me, doctor.
Right. Yep.
This part was pretty algebraic, so I understood this part. Yeah.
Okay, good.
Hmm.
Good, good, good. Okay, so So that means that f prime of x, if I use the prime notation, is going to equal 2x minus 7. Okay, so then I say, all right, let's use the power rule to take derivatives instead. So I kind of give you, this is the example. So if you have some constant, and this is raised to some power n, that is a perfect example of when to use the power rule. So what you do is you take the power, bring it in front. Now it's being multiplied, and then you reduce the power by 1. So that's how we do it. So let's see if we can do it on this problem. So if I have f of x, and that equals x squared minus 7x plus 3, then the first derivative, if I use the power rule, what's going to happen is you can apply this power rule to every term, just go from east to west. So this first term is x squared. So I would bring down the 2, write the x, and then this technically would be to the first power. After you get in the habit of doing this, you don't have to put a 1 up there, but you can see how it follows the pattern. So then what happens here? So let's see. We should have, this is raised to the first power, right? Because if there's no 1 there, it's kind of there. So follow the rule. 1 times this -7 is going to be a -7 still. Now I write the x, and 1 minus 1 gives me x to the 0. That's why that works out. Okay, and then if you think about this constant as being 3x to the 0, the second you bring this down, you're going to have 0 times a number. So this piece is going to be 0. So when you start out, you can see now that my derivative that I got using limits, I have the exact same thing here. And remember, x to anything to the 0 power is 1. So that's why it's just 2x minus 7. Okay, so much easier. So now that you know the power rule, when you do a limit, and you're going to have to do that for like the test, you can check it and know where you're going. It's like having a map, so if you don't get the answer that you think you're going to have, it's a lot easier to go back algebraically and say, okay, where did I make an error perhaps? Because I know what the answer is going to be now, and that's a better position to be in. Okay, so then I said, let's practice doing the power rule. So if you're doing this first one, we're going to always use the prime notation, or at least right now we are. So here is your constant, so that's your k, x to the n. So your derivative is going to be n times k, which is 2 times 14. So I'm going to just write it like this for right now. And then you're going to have it be x to the 2 minus 1. So that just gives you f prime of x equals 28x. And x is to the first power, and that's what you can do. So if you had done the limit of this as h approaches 0 and did the whole change in y of a change in x, this would be your answer. Okay, and it makes sense in that this is a quadratic because it's squared, and your derivative is linear. So that also kind of affirms that thought. Okay, so for the next one, this is a line. So the derivative of a line is going to be 1 power lower. So if this is to the first power, then it's going to be to the 0 power, which means it's going to be a constant. So when I take my derivative, it's going to be 1 times 2. So I'll just do it kind of all written out. 1 times 2, and then I'm going to have x to the 1 minus 1. And then this is minus, this is really x to the 0 when you think about it. So 0 times 5 at that point is going to be a 0. So this falls away, and this ends up being just 2x. And that's, excuse me, just 2. Because x to the 0, which is what this was going to be, is going to be, let me just do that. So this is going to be x to the 0, because 1 minus 1 is 0. So you can just write your final answer as 2. And that makes sense because, as I said, it's a step down. So here comes another parabola, and this is a good candidate for doing limits. And when you look at that, see if you can go ahead and take the derivative. So I'll do it and not say anything. Whoops. Are we good? Okay, so now we come to this next example. And radical symbols are not our friends when we're taking derivatives, when we want to use the power rule. So your first step is to make this into a fractional exponent, because fractions are indeed our friends. And so this is going to be to the 1/2 power. You've got to do that first. So get comfortable with all those fractional exponents. So then now we're ready to take our derivative. So that's just going to be 1/2 x, and it will be to the 1/2 minus 1. So you're going to end up getting, and this is 1/2 x to the negative 1/2. Now that's a fine answer, and that's really the best answer for our class, because if you wanted to do anything else with it, it's better to keep it in fractional exponent form than it is to change it back to a radical. If you, for some reason, you had to change it back to the original form, you would have be 1/2 radical x. But you really would only do that if they told you that you had to return it to the original form. Otherwise, having negative exponents is fine in calculus. I know, like when we teach pre-calc, we don't let them have negative exponents. We make them put that into the denominator, but in calculus, it's a different story. So then this next one, so are we okay with that if I have a power? So if we do this next one, you have to know what goes where. So the index number, so this little guy is an index number. So the index number always goes in the denominator. Or if you want to think about this as being a smaller number, one could say a baby number, you can say baby in the bottom. That's another not professional way to do it, but however you remember it, it's a good thing. So this is going to be x to the 4/3. So then your derivative, and remember, notation is really critically important. That's going to be 4/3, and keep it as a fraction. Don't turn these into decimals because it's going to be irrational for 1. So 4/3 x, and then you're going to say 4/3 minus 3/3. So you're going to raise this to the 1/3. Okay, is that okay? Okay, so then what always kind of confuses people is when we have irrational numbers like here and here. So the key is knowing that it's a number and it's not a variable. So you're going to treat it like a number and not like another x term. So you can just work from left to right, and I can do it right underneath it because sometimes it's easier to follow it. So that's going to be, I'm going to bring the 3 down, 3 times 12. I'm just going to jump ahead and just call that 36. And then this is x squared minus 4 times 6 is 24. And then that's x cubed. So now when you get to this, the x has the power of 3. So you're going to bring the power down in front of pi, which is just an irrational number. Continue with the x and reduce the power by 1. Okay, now we have e, which is another irrational number. So you're going to bring down the 2, and then you're going to have this be e, and then you're going to say x, and you're going to have 2 minus 1, so that's to the 1. then this is no x involved, so it's really x to the 0. So therefore, doing the power rule, the first step multiplies a term by 0, which is just 0, so it's going to disappear. So at this point, you can start saying the derivative of a constant is 0. And it's because a derivative is a rate of change, and constants by their natures never change. So its rate of change is 0. Okay, does that make sense? Okay, so now there are many rules in calculus, but you don't have to use them all. You want to always use the rule that's going to make your life easiest. So you would be well versed to change this. Now that 2 is not associated with the x cubed. It's going to stay in the denominator. So that 2 is staying right here. Because you basically have a half as your multiplier. So then you're going to bring up the x. When you bring it up from the denominator, the sign goes to negative. So that's the best way to write that. Now you're ready to take the derivative because you can use the power rule. So f prime of x is just going to be -3. I'm going to bring the 2 along, and then this will be x, -3 minus 1. It goes more negative, so it's to the -4. And that's another mistake that a lot of times my kids would make, is that they would make it -2. Okay, so that's the best way to handle it. Now, later on tonight, we're going to learn about the quotient rule, but you probably would not use the quotient rule for this. You would probably just do it exactly like I just did it. And then finally, we can say that, oops, my notation was not, no, my notation was good. Let me leave that be. Okay, so now, at this point, you can start saying a derivative of a constant is always going to be 0. Okay, and another reason why you want to think about that, remember how a derivative is just a slope. So if this is f of x equals 100, and I'm asking you for the slope, which is the rate of change, the slope of a horizontal line is 0, so that's how it all makes sense. Okay, was that a good way to bring it home? So always think about derivatives as being slopes, because that will sometimes give you a good insight. Okay, so as I said, this is a night of rules. So there are a lot more rules, and our textbook doesn't do any of them. So this is one of them. So this whole page was the power rule. So I want you to be able to use some of the calculus, because just, applying some of these rules, even if your kids didn't totally understand it, you could do it at different levels and just say, okay, this is the rule, how would I use it? Because the more they can be familiar with different concepts in math, it's okay. So here is the product rule. So when you use the product rule, when you have function times a function, so that means both of these have x's in them. You wouldn't use the power rule if you had a constant times a function. Then you would just use the power rule and not the product rule. Okay, so here's your rule for your derivative. So to find the derivative of this expression, you do, this is the left, so left, d right, which is left times the derivative of the right, plus the right function times the derivative of the left. So you can abbreviate like this, but you can kind of write it left derivative of right plus right times derivative of left. Okay, so then how do you know how to keep it straight? Always start with an L sound, because when I do other rules, it's going to start with an L sound as well. So start with an L sound. So this is an example of when you would use the product rule. And would you really use it? You probably wouldn't have to, right? Because
Professor,
couldn't you
question.
multiply and change that? And make
Dr. Riley,
and use
question.
the power rule? So I just
Um,
use this as an example so we can also check our work. So if I said that this was your g of x and this was your h of x, the most efficient thing would be to change it and do the power rule. But let's do the product rule just so we can practice. So it's going to be, so f prime of x is going to be left. So you write down the function on the left, d right. So 3 times 8 is 24, and then you take x and lower it by 1. Okay, and then you're going to add, so we started out with left, so now we're going to say right. So this is the right function, and we're going to say d left. So that's going to be also 24x cubed. Okay, so then if you figure out what this is, 6 times 24, the 4 carry the 2, 6 times 2 is 12, 144, and then you write the variable and you add the exponents, plus that's 32, carry the 3, 16, 17, 18, 19, and then you add the exponents, right? So then you can add the coefficients, so that's going to give you 6, 9 and 4 is 13, and 3. So did I do my math okay?
yes.
Okay, so I get that, okay? So that's a fine answer. This is f prime of x. So as I said, there's gonna be lots of rules. You don't have to use every rule, because if I can just break this down, isn't this equivalent to 48 x to the 7th? Right, because I can multiply the 6 and the 8, and then I can add, I write the x down and I add the exponents. So if that's my f of x, then my f prime of x, if I want to use the power rule, and I can even use it just to check my work, that's going to be 7 times 48. So 7 eighths are 56, and the 6 carry the 5. 7 times 4 is 32. Excuse me, 7 times 4 is 28, and 5 more is 33. And then lower this by 1. So I get the same answer. So I demonstrated that I understand how to use the product rule, but I checked my answer using the power rule. Okay, so clearly after you know all the rules, you're going to pick and choose what's the best thing to use. So unless I say, I want to see how you would do this using whatever rule. So if we're going to continue practicing the power rule, or excuse me, the product rule, we have to first rewrite this, right? Because what's our problem? So what do you think, what's the problem?
There's a square root.
Right, so I had to raise that to the 1/2 power.
Mhm.
So I'm going to first rewrite it. And again, notation is really critically important, because when my kids get lost, that's where they get lost, in not having good notation skills. Okay, so I have that. Now, again, I could have combined like terms and made this simpler, but let's just do it to practice. So if I do the product rule, I'm going to say left, d right, plus right, d left is going to be 1/2, and then x to the negative 1/2. Okay, so that's going to be 30x. So that's going to be the 9/2 plus, and that's going to be 3x. And if I do that and I add that, it's also going to be 9/2. So it ends up being 33. Oh, sorry, 9/2 is what I wanted to write. Oops, 33. Let me just get rid of that 4. So it's 33 x to the 9 halves. So did I do that okay? Let me just see what I have. I should be checking my notes. Yep. So we're okay. So what is that? Remember, if they said write it back in radical form, you would say that's 33. Whoops. 33. And then this would be x radical and then a 9 power. Because sometimes in textbooks, your answer would be like that. So this would be the final answer. So we could go through and do it the other way and make sure that we will get the same answer, but I'm telling you we will. So now this is a more complicated thing. You could also distribute and kind of clean everything up, or you could just go ahead and say, I'm just going to do the product rule for this. So let me just do it. I'm not going to say anything, so you can look up and see how you're doing. And I would use parentheses. And then we would go beyond that point and kind of clean things up. But for our purposes right now, I would say just stop there.
Okay.
Because ideally what you would do is you would first look, and if you could factor out anything, you would do that. Instead of like expanding it, you would try to contract it. But since I can't factor anything out, we're just going to leave it the way it is so that you've at least practiced doing the product rule. Okay, so this one also, you have this x that's in radical form in the denominator. So you want to think, okay, I know it's to the 1/2, but since it's in the denominator, I have to bring it up as x to the negative 1/2. So I first would have to rewrite the problem. So once I rewrite it, then I could do the product rule just as an example. So you could get it all the way down to there. And if you had a textbook with answers, that's probably the way they would give you the answer. So I think I have 2 more of these because I think I was going to play around with, can we clean this up a little bit? And what could we get? Because once you start taking derivatives, you kind of want to always be at the position where you can take another derivative of that. So for example, if we had that in mind, we would definitely have stopped at this point, right? Because at that point, and that was not a good thing, I'm not gonna underline it. At this point, that's where you could take another derivative. Whereas the final answer of 4 over radical x, that's a good final answer. But if you had to move further, you would use the 4 times x to the negative 1/2 form. Okay? So
Mhm.
let's do, would you guys want to do the other two?
Sure.
Kind of talk about it? So I can put you into a meeting room. So let me stop sharing for a second. And let me just do that so that you can actually talk and meet with each other. Okay, so I'm going to create only one breakout room. Okay, so go ahead and hop in, and I'll do it here. And then when we come back, we can all look. Okay, good. So let me make this bigger. Let me go back to sharing this.
Yeah.
Okay, so now we have to play the matching game. So see what you did. What I started doing is I started changing colors so that you can see where I multiplied the right pair versus the left pair. Now, knowing it's been a long day, I'm hoping if you can find an error, I'm okay with that.
Mhm.
So ideally, you want to see if you can factor something that they have in common, but the way I've set it up, nothing was in common. So then your next thing is to think, I might need to take the second derivative, which is just means you take a derivative again. So I wanted to get it in the best form to do that. What do you think? Do you see anything?
Hmm.
Okay, there. Okay, there. Okay, so that purple looks okay.
Mhm.
Okay, that looks okay.
Mhm.
And so you can see there's so much algebra involved in the calculus. So are we getting the gist of it?
Yes.
Okay. All right. So then let's go ahead and we'll do the quotient rule, which is the next one. And then we're going to do one last one, which is the chain rule. Then we'll have all the basic rules. And so we're not going to go too crazy with this. So this is when the setup for the quotient rule, when you have a fraction, a function over a function. So this is how they do that. So remember, start with the L sound. So the L sound's going to say, oh, this is high, by the way. So this is high, and this is low. So you would take low, so take the hx, multiply it by the derivative of the high. So low d high minus high d low over low squared. Okay, so low d high minus high d low over low squared. Kind of has a little sing-song movement. So the key is you have to have a fraction for your answer, and this time it's a subtraction in the numerator. Whereas before we did lefty right plus righty left, so you had an addition in the middle. And those are the two areas that my kids usually would mess up in. So given that that's our formula, so you would say, okay, then f prime of x is going to be low, which is just write out the low. Put it in parentheses because it has more than one term. D high, so that's going to be 7 minus high, write out the high, put it in parentheses just to keep everything squared away. And then D low, which is just 8, all over this term squared. Okay, so since you have to have the rule of 3 to try to remove something through common factoring and then canceling, but since we only have 2 that are the same, we have this one and this one, we can't do it. We would need to have it over here as well. So we know we can't remove anything in this format. So what we're left with is we have to combine terms again. So you would get 56x plus 35. I would keep it in parentheses. minus, and then that's going to be 56x. And then do not square this. I do not do not multiply it by 8x plus 5. Just leave that be. Only work on the numerator to combine like terms. So that's going to be, looks like 56x minus 56x. So I'm just going to have 35 in my numerator over 8x plus 5 squared. So what do you think about that rule? So you
Mhm.
just want to remember the sing song. And if you always start with the L sound, that will get you started. So if I'm going to do the next one, I would say low, in parentheses are definitely your friend. Low D high minus high D low, which is just 1, all over x minus 5 squared. Again, if I had an x minus 5 in 3 places, I'd be able to factor it out and cancel, but I don't have that. So I'm just going to only focus on the numerator. I have x minus 5 squared, and then that's going to give me 14x squared minus 70x minus 7x squared, again, minus 2. So again, distributing that negative is where my students would tend to mess up. So I can combine like terms. That's going to give me 7x squared minus 70x minus 2 all over x minus 5 squared. And that's the best I can get it. Then there's another one here. There's 2 more left. And the last one has a pi in it. So I wanted to make sure that you are comfortable handling the pi again. So do you want to do the same thing? Should we just break and you two can talk about the last 2 and I'll do them and then we'll come back again?
Sure.
So you don't have to just always listen to me. So let me stop sharing. Okay, so I think we can say, how are we going to do that? So I have a room in progress. So okay, so I think you got invited to join the room.
Mhm.
So go ahead and I'll do it on my own here. So how did everything go with the pie, especially in the
Yep.
lab? Okay, good. Did we lose Poonam?
No, I'm here.
Okay, okay, yeah, hold on a second. Let me just see if I can figure out how to do this. Okay. All right, so that's what I got.
Mhm.
Am I okay?
That's
You-
what I got.
Okay, perfect. Let me do that. Okay, good. Okay, so yeah, that's what I've got. So be careful about the pie. Other places that are red flags, just distributing the negative has always been a problem from my calculus kids in high school.
Mhm.
So just be careful about that. And that's why I'm like obsessive about using parens until I really see what the problem is. And
Mhm.
then I drop them as need be. And again, if I ever had a piece in the denominator that I could factor out in the numerator, I would do it, but we haven't had any examples of that here. So never never make that denominator more, never expand that denominator, leave it the way it is. Just always work on getting the numerator squared away. So anyway, that's good. So we have one more rule, and then after that, we're going to do some analyzing of functions. So here's the chain rule. So you use the chain rule when you have a function raised to a power. So what you do is you do the power rule outside, and then you come back inside. So use the power rule here and then come back inside. So for example, here's a function raised to a power. So you're going to use the power rule. So bring the 6 down in front and then go ahead and raise it to the 5th power. Now look inside and take that derivative, and that derivative is just 3. Then the 3 and the 6 can combine, and your final derivative is a constant times a function raised to a power. So you have to use this whenever you're using the power rule, but what your base is a function itself. So then here are just a couple of examples. So this is pretty straightforward. You just change your notation, do the power rule first, don't touch anything inside. And that's the other thing. My kids sometimes will start touching things inside right away. You've got to refrain from doing that. Just do the power rule only, then look inside, and then combine like terms from the front and the back. And then don't forget, it's still raised to the 4th. And what do you think about number 2? That's my trick question.
Hmm.
So what's this derivative going to be?
It's interesting.
0, 0.
Right, good, because it's just a constant, right? There's no variable there. Okay, my kids would get so much to work. They'd be so proud of themselves bringing that 4 in front and doing the whole thing. So yeah, so just keep an eye on that, recognizing that pi is just a number like anything else.
Dr. Riley, I don't think we are sending you any calculus kits. Our kids cannot do two-step equation. I am not lying. Two-step
Yes.
equation.
Some of them can't even do one-step equations. Some of them
Yes.
look at an equation and go, what's the x?
No, and some of them, if you tell them like, hey, today I was doing a problem with speed. The speed is distance divided by time. So there was
Right.
time missing. Sometimes distance was missing. Speed was given. They could not even like write down that equation, like a speed, number, distance, and the t. Couldn't.
You come to our class last week, right, Sarah? We were doing that.
Yep. Sometimes the kids can't even multiply single-digit numbers. I'll be like, hey guys, what's 9 times 3? Silence. I'm like, guys,
Yeah.
do we not know our times tables? We sure don't.
I know. Yeah, no, sometimes it's super, super challenging. I am finding that it's a little bit better now than it was right after COVID. Have you seen the difference there? Because that was horrendous right after COVID.
Yeah. Oh my God, that was so bad.
So bad.
That's when I started teaching. It was, oh my God.
Yeah, you think, do they know anything? Like what happened? What happened? But yeah, that was awful. They got really good at cheating.
Oh my God, yeah.
Now everybody cheats. That's it.
Yeah, but at least we're not in the COVID world where it was, oh my gosh, it was so hard to keep them from themselves. Okay, if we have this little puppy here, that's a big old 6. Now, always look inside because sometimes they don't combine things and you can always, combine like terms, but there's no like terms in here. So really restrain yourself from doing anything with that. Just copy it the way it is. It likes to be left alone initially. And then again, parentheses are your friend. And I'm just going to leave it like that, because distributing the 6 in all those 3 terms is not going to make my problem any better.
Mhm.
So I would leave that be. And then this I put in because I wanted you to remember, oh, right, radicals are not, conformable to using the derivative rules. So my first step would be to write it to the power of 1/2. And then here we have 1/2, and then we have 5x squared plus 2, and this is to the negative 1/2. And then that's going to be times 10x. And then you could, clean that up a little bit because you would have really 5x in front. And then if you really wanted to kind of go back to the original form, you could. Because that's what that would look like. And that probably be the way that a textbook will give you the final answer. And then this one, I wanted you to remember that, sometimes you have an index number other than 2. So first step, and a lot of times my kids, the other thing they would make a mistake with, their first step, they would rewrite it, but they would indicate with that it was a derivative. And they know they didn't want to be a derivative, but they started doing that, and then it kind of messed things up. So remember, when you write it over, it's still the original function. And so this really is to the 2/3. Okay, so then you're not quite done because you're going to multiply that by 7. So then 14/3. And then you could put this down here if you knew that your problem was done. And that would be your final answer. So those are all the rules. Then I wanted to show you like how you can use these kind of things to analyze a function and kind of figure out what it looks like and then perhaps graph it. So that's what's coming next. So we had what, 4 rules: power rule, product rule, quotient rule, and chain rule.
Mhm.
You want to commit those to memory. So here it says they want you to analyze function using calculus. So given the function, so you can see right away it's going to be a quadratic. Okay, and quadratic, yeah. So yeah. So anyway, what's going to happen now is it's going to be a quadratic. You could factor it, right? So this is going to be x minus 5, x plus 4. So I could do a lot of graphing it based on what I just did. Because I know that I have 2 roots. One's going to be at -4. One's going to be at +5. I know my intercept is going to be at -20. So my function's going to look like this. The only thing I'm not getting from this form is perhaps the vertex, which I could play with. But let me show you what you can do with calculus. If you take the first derivative, so taking the first derivative, you would say, okay, f prime of x, this is just your basic power rule.
X minus 1.
And if you take this derivative and solve for 0, set it equal to 0 and solve, you get 2x equals 1. So x equals 1/2. So what does that do for us? Well, that X value is the X value of the vertex. So that's kind of nice to know. So this is the X of the vertex. So then what you can do is you can say, oh, well, that's really cool. So now what I'm going to do is I'm going to say, could I do a sign test to see what's going on with this? So if you do this, put your 1/2 right here. And then what you're going to do is you're going to figure out what the function's doing on either side of that 1/2. Now, why am I doing that? Well, I want to see whether my vertex is a U-shaped, part of a U-shaped function or part of an upside down U-shaped function. So if I'm going to evaluate 1/2, I take my derivative and I figure out a number to the left of 1/2. So your best number really is 0. If you plug in a 0 in for 2x minus 1, then you're going to get a negative value. Doesn't matter how negative it is, just put a negative sign. If instead you check to the other side, and let's have our critical number that we're going to test be a 1. If I plug a 1 in, I'm going to say 2 minus 1, that's a positive number. So this is called a sign chart. And so what I'm seeing is to the left of the vertex value of x, my slope is negative. So that looks like this. Then I get down here and I know it's 0. And so the base of it, the vertex itself, has a slope of 0. It's not changing. And then to the right of it, it goes positive. So see how that traces out the shape of my parabola just by using calculus? So then what I can do is I can say, so let's do some vocab. This X is the vertex, but it's also called a critical value. Critical values happen when your first derivative equals 0. So they're the X's that make your first derivative equal 0. Doing a sign chart tells us the action on either side of that. So then if you take the AP calculus test, you could do a sign chart, but that would not be sufficient. You'd have to write out an explanation of it. So you can say to the right, excuse me, to the left of the critical value of 1/2, the slope is negative. To the right of the critical value of 1/2, the slope is positive. And then you can say, since the slope changes, and that little triangle is my changes, from negative to positive, therefore, we have a min at x equals 1/2. So that would be your statement. You'd have to explain that you tested the slope on either side of that critical value, and that pattern of negative to positive traces out a minimum. So then based on that, you could do some graphing. So what I know at this point is so let's write our initial equation, x squared minus x minus 20. So I could factor to find the roots. So I did that already. X minus 5, x plus 4. So I've got these roots at plus 5. So 2, 4, 6. So that's going to be right here. And then I want to be -4, which is right here. Then I also know my y-intercept has to be 20, so that's here. And then I know that my minimum is at 1/2. So that's going to be either on either side. So let's figure that out. If you evaluate the function itself at 1/2, you can figure out what your value is going to be for your y. So you'll know how far down you're going to go. So it's clearly going to be on this side because my x is positive. But if you plug it in, so I have 1/2 squared minus 1/2 minus 20. So that's going to be 1/4 minus 1/2, which is going to be negative 1/4 minus 20. So this value is going to be negative 20 1/4. So now I know where my minimum is. So based on factoring, analyzing the equation, and then using calculus to analyze the vertex, I now can trace out the shape. So this function is f of x. And then Sarah, once we have that function, we can also get the function of the first derivative. Because we're just going to figure out where that's going to be. So that's going to go through this point right here at 1/2. And it's going to be, let's see, if my slope to the left is downward facing, it's going to go like this. So this would be my first derivative. And that's the line that we discovered above. So you can kind of tie in some of the stuff we did last time with this. So I had a couple of more little problems. The next one is kind of like this. So this is kind of the same. So let's just say you probably could do that. Just model after the first one, because I don't want to take too much of your time. And if we have time, we can go back and do this again, but it's the same idea. It's a parabola. Your first derivative is going to give you a linear function. You're going to set that equal to 0, that you'll find the x of the vertex, and then you'll do a sign chart to figure out if it's positive or negative. So if it's a downward facing or an upward facing parabola, we already know it's upward facing, so it should be a U shape. And then you follow the exact same steps we just did. But I do want to get to these are two different ones. So if I give you, so I'm going to erase this because I give you something here. Let's see, what do I want? Because I've done this already, so I want to just erase this and start from scratch. Okay, so this is a really cool use of calculus. So we can do a lot with limits in here, but we can also use our rules. Okay, so if you have the situation, a homeowner wishes to build an above ground pond enclosure in her yard. She analyzes her yard and determines that a 10 by 10 foot square plot would be the best location. Okay, so she's gonna have a 10 by 10. So here's your plot. So from here to here, it's 10, and the units are feet. And same thing here. She plans on putting lights in the 4 corners by building square boxes of an undetermined height and then matching this height to a border built around the enclosure. If she wishes to maximize the volume of the enclosure, at what height should she build the light boxes and the border? Okay, so let's think about this. So I want to build these little square boxes, so I'm going to indicate that these are square, and I'm going to do it by doing that. Okay, so then the other thing I want to do is I'm going to just pick a variable. So since they're the exact same squares, you can make that x and that x. And then because it's square, these will be x's also. So in order to figure out your volume, envision that you're going to fold this up. Okay, so if you envision that you're folding it up into like a box, so what you're going to find is the volume is going to be length times width times the height. So I'm not sure what the height is going to be, but I do know the length and the width. The whole thing was 10. So this is going to be 10 minus 2x. And this will also be 10 minus 2x. So I have 10 minus 2x times 10 minus 2x, and then my height will be the x, and that's the unknown. And my job is to maximize volume. So that's interesting. So let's think about this. If I multiply these together, what I'm going to get, so I'm going to cut to the chase here a little bit. But let me just do these two together first. So that's going to be 100 minus 40x plus 4x squared, and then times some height. So that we can go one more step. So what I'm seeing is that this is a cubic function. And when you maximize, so if they tell you to maximize, you're going to take the derivative and set it equal to 0. So let's see if we can take that derivative. If it was a cubic, then I'm assuming, oops, that my first derivative is going to be a quadratic. So it's going to be what, 100 minus 80x plus 12x squared. Okay, so hold on. Did I do something incorrect there? So I have 100. Okay. Okay, what was I thinking here? So my volume is that. Okay. Yeah. My volume is that. So I definitely have 100 in my thing. So I have that. So let me see if I wanted to think about what I was doing here. So can I factor anything out of that? I don't think I can. So this didn't turn out the way I wanted to turn out. So what happened here?
Could we use the quadratic formula?
We could.
Dr.
We
Riley,
could.
one question.
Uh-huh.
You said that even the height is not known, so we are keeping it as like a cube.
So it's a variable. So that's your x, right? Your x is your height. Because remember how when you make your little boxes in the corner,
Mm-hmm.
that's going to be when you fold it up, kind of. So I don't think this is a good problem the way I have it written. That's my main problem.
Because I was thinking, like, if you look at the x, that looks like width. So
let's see.
I mean, it makes sense to me if you're saying that the height of the box is matching the unknown length that you're making the square boxes.
Right.
yes.
Right. Yeah, it is. Somehow I dropped out my 100, and so I had a much nicer answer. So how could I do that so I can show you this lovely answer that I had?
Hmm.
Well, I guess what we would have to do is we would have to do the quadratic formula to get your x's. Then what you would figure out is, so this is the basic theory behind it. You would have to do a sign chart, but instead of having just one value, you would have two. Okay, so let's figure out what that is. Let me just grab my calculator and we will do it the old-fashioned way. So I want to know what the two roots are. So why don't we do it by putting it into a graphing calculator and saying, so y equals this. So I have 12x squared minus 80x and then plus 100. So if I graphed that, I want to see where a cross is. So I have a crossing two places. So I'm going to say second calc, and I'm going to find my two values. So I'm just going to give you the two values. So second, graph, second calc, and I want to know the zeros of the function. So left bound, right bound, enter. So one of them is 1.66. So this is going to be 1.6 bar notation. We find the other one, second calc, and value, the 0. Left bound, right bound, and the other one's going to be 5. Okay, so I've got those two values. So what I'm going to do, I have my derivative. Let's go ahead and we're going to analyze. So pick a number. So why don't we pick the number 0, because that's a good critical value. If I plug 0 into the function, what is my value going to be? It's going to be positive, right? So that's going to be a positive. Okay, pick a number between 1.6 and 5. So let's say I have a 2. So I plug in a 2 as my critical value, and I'm going to get what? 48 minus 160 plus 100. So that's going to be more negative. So that's going to go negative. Okay, this is how the slope is going. So if I pick a number bigger than 5, 6, when I plug it in, my slope will be positive. What does my shape look like? So it looks like this. Positive, it goes to 0, it goes negative, comes down to here, and then it's going to go positive again. So here's negative and then positive. That's what my function looks like. If I want to maximize my height, I want to say set your x equals to 1.6 bar to maximize the height. If I want to minimize the height, set your x equal to 5 to minimize the height. So you can use a sign chart to analyze the function just like we did previously. And then there was one other problem that was a business application. So with the business application, so do you have what you need here? We took the derivative. We then found the critical values. So these are critical values right here. So these two numbers are our critical values. we put them on a sign chart and analyze the result on the slope of putting in test numbers on either side of the zeros of the function. So that's what we had done. And then the very last thing I wanted to do was this. This is another business application. So if you're using calculus to figure out revenue, okay, so revenue equals price times quantity. So if you know that revenue equals price times quantity, and they give you quantity and they give you price, to maximize your revenue, you're going to multiply those two together. And then you want to maximize it. Maximize always means the same as minimize. You're going to take the first derivative, second equal to 0, get your critical values and analyze them. So here comes my total revenue. So I have 15 plus 30x. And then this is 4 minus 0.8x. So when I could do the quotient rule, or the product rule, or I can just multiply it out, which is more efficient. So if I do that, I get this. So I just multiplied it out because I said, yeah, I could do the product rule, but I'm thinking that it may be easier for me to do this and then take the first derivative. Okay, so total revenue, if I put it in order, so in standard form, that's going to equal negative 24x squared. And then if I combine these two, it's going to be plus 108x plus 60. Okay, so that's my total revenue. Now take your derivative. Total revenue prime is just going to be minus 48x plus 108. So if I have just that, then I need to figure out, okay, set this equal to 0 and solve. So what do I know? So I have 48x equals 108. So I'm going to say 108 divided by 48, and I'm going to get, oops, sorry, second quit. 108 divided by 48. And I'm going to get 2.25. So when I set this equal, I get x equals 2.3, say. Okay, so now the question is that going to maximize or minimize my profit or my total revenue? So do your sign chart. Oops. Oh, my goodness, hang on one sec. There we go. So I don't want to have that line there. So here's your critical value, right? You got that by setting your derivative equal to 0. So that's your critical value. Take a sign chart, put your critical value here. You're then going to analyze your function on either side. So here is your first derivative. So pick a number to the left of 2. You can pick even 0, which is nice. So I'm going to pick a value of 0. I'm going to plug it in, and I get a positive number here. If I put in instead a 3, whoops, I don't want to put it there. I want to put it here. What happens is I get a negative number. So my function, my original function is going to look like this. It's going to reach a max at 2.3. So I know that if I sell 2.3 units of goods, I will max profits, or max total revenue. Okay, so that's how you could use this to figure out how to max things. So that's the total revenue. So then you would have to do a statement with your sign chart. So at the critical value of 2.3, the slope changes from positive to negative, and therefore 2.3 yields a maximum. If I found that it went from negative to positive, it would yield a minimum. So that's what I should produce if I want to maximize my total revenue.
Does it matter whether we express the answer as 2.3 or 2.25? Does that make a
It
difference?
doesn't- No, it doesn't matter.
Okay.
So that's all I wanted to cover tonight. So it's kind of a lot because we did all the rules and then we did this business application, which comes in very handy when you are figuring out total revenue or even profits. And there are other things we can do with that to play around with it. But it does come in handy to be able to do these critical value tests. That's called a first derivative test. There are second derivative tests that we may or may not get to, but that's how you can do some graphing without actually putting things in your graphing calculator. Since you know the root, the fact that the critical value is the X value of the vertex is very helpful. So there you have it. So I will post this video and then I'll also post my filled in notes. So they'll be up under, I think, pages, wherever I put them last time, that seemed to be good.
Yeah.
So there's nothing due next week. So just kind of, process this, see where you are with it. And then we'll meet next week. That sound okay?
Yeah.
So I held you a little bit over, but I knew I was short last week because I knew that this was coming.
Yeah.
So
So Dr. Riley, so I can upload everything till now by like Friday or Saturday. I didn't get a chance to like look at stuff also.
yeah, look things over. You need to do the first problem set, but look at the notes first
Mm-hmm.
because that's up there.
Mhm.
And then you can look at the filled in notes as well as look at the video. And then
Oh,
there's
sure.
a journal article that's due as well. So, and then there was a first problem set too. So you're 2 problem sets behind.
Okay. So will it be okay if I do it by Friday or Saturday, upload everything?
Yeah, why don't you say like maybe by Tuesday, everything is up? Okay, so then when we come to class
okay,
again, I know
perfect.
it's up.
Yeah,
And
yeah.
then
Thank you so
I'll
much.
grade as I can.
Okay, okay. Thank you so much, doctor.
Okay, you're welcome. And I'm going on junior retreat for the next 3 days. So I'm going to be looking at whatever's posted over the weekend. So just know that, Sarah, that I won't probably get to it tonight because I like to do it right away, but I'm going to be out of town until I get back on Friday night.
Yeah, take your time.
Okay. Okay. Well, thank you. Well, so this was good.
Yeah.
So welcome aboard, Hunan.
Yeah, thank you. Thank you.
We're deep into it.
This is perfect. Who
Yeah.
wouldn't dream of having a class with just 2 people?
Like 2 people. Yeah.
I know.
I
No,
mean,
it's great.
I dream about it. I don't know. The students get scared nowadays. They're like, "Oh my God!" It just
No place to hide.
Yeah.
I'm
I
like,
know. And
I
hopefully next
dream.
week we'll have Sarah too. So you'll meet, excuse me, next week we'll have Catlin. So you'll meet Catlin in addition to Sarah.
Okay. Yeah. Thank you so much,
Yeah,
doctor.
you are
Good
very,
night.
very good. So have a good night, guys. Thank you for
Yep.
hanging in there and doing all that writing.
Thank
Yep. See you next week.
Bye-bye. See you next
Bye.
week.
Good night.